Thank you, Chat. That was a wonderful introduction, and so I can skip through the next couple of slides. Um, so as Chat said, I'm James Eagan from Télécom Paris and the Institut Polytechnique de Paris, which, interestingly enough, neither of which is directly in Paris, but so it goes. I'd like to talk to you today about reinventing the mind's bicycle. And so I think I can skip through this part, but as Chat said, so I did my Ph.D. at Georgia Tech, and before that I did a math computer science degree, a bachelor's degree at Lawrence University in Appleton, Wisconsin. So I come at all of this from the perspective of a computer scientist working in human-computer interaction and sense-making. So I want to start with a story. There were some researchers who were trying to figure out which animal is the best, for some definition of best. And so they created a plot that looked at the speed and energy efficiency of different animals. And on this curve, you would find at the top the sleek, elegant animals that are really fast and efficient, hawks and cheetahs and beautiful animals like that. And humans, us, were only fairly middling along this graph. But somebody said, hold on, what separates us from the animals? Okay, well, there are a lot of things, and it turns out that the fact that we use tools doesn't really work, but let's work with this. And if you give a human a bicycle, suddenly our locomotion just goes way up. And so when Steve Jobs was asked to describe what is a computer, he basically said that what a computer is to me is it's the most remarkable tool that we've ever come up with. And it's the equivalent of a bicycle for our minds. And so if we think of the computer as this sort of a bicycle for the mind, as a tool for people, this is a great tool for interacting with and manipulating things. When we're talking about the computer, things are, of course, data, but it's also a tool for understanding and for communicating. The problem is that it's still a fairly rudimentary tool, and we need better tools. We need better tools that let us improve the interactive bandwidth that we have so that we can more expressively learn and master and align those interactions to the specific needs that we have with our data. And there are a lot of people within the research community who are working on this, on building better interaction techniques, better interaction devices that address these problems. But we want these tools to also be something that the user can appropriate, that the user can adapt to their own needs, that you can take ownership of and adapt them to ways that you see fit. And there are not as many people who are working on this part. Although, interestingly enough, back in the 80s and earlier, there was a lot more experimentation going on this kind of work. And then the last part is to amplify cognition. So globally, to fit within the larger sense-making process. And as Chad alluded to, I do a bunch of work on all three of these parts. Today, I'm not going to be talking so much about this, but if you're interested in it, I would be happy to talk with you afterwards during the break. So let's come back to this bicycle. The problem is that today the computer that we're using is still more or less the equivalent of the penny farthing bicycle. Now, maybe we're used to bicycles that look a little bit more like this. They look a little bit different, but the fundamental principles really haven't changed a whole lot. You might have a bicycle that's great for getting to work. There are different models, so you could have a racing bike. You could have a model that lets you take your whole family around for a nice Sunday joyride. I took this photo this morning as I was coming in. Somebody had actually added a couple of attachments to their bicycle, bought a carriage for their child, presumably a smaller child also for the car seat, or bike seat. But someone had to basically find these plug-in attachments and make this better. Another one that I saw this morning was the post office has this fancy custom bicycle for delivering the mail. On the other end, we see for example, BMX bicycle riders that adapt themselves their own bikes, such as by welding on bits and pieces so that they can do acrobatic tricks and adapt their bicycles in their own ways. Or a coffee peddler who might want to blend their bike with, say, a wheelbarrow and a cabinet so that they can take away their coffee machine and sell coffee on the square. But if we look at software, turns out that software doesn't let us do that very easily. Software is not so soft. Most software is designed around the idea of creating something that is suited for a large number of users, that can do most of what they need, but none of you is all alike. We're all different. And so oftentimes we find ourselves saying, well, if only this software did this extra little bit. How can we do the same thing, graft on new footpads to our BMX software? Let's do that same software. How can we modify it so that we can add in that last little bit of interaction or that new little bit of functionality? So let's make software malleable. One of the questions is, how can we realize that goal? So one approach is to say, well, what if the toolkit, the tools that software developers use, actually had these kinds of hooks to allow this kind of extensibility built directly into the toolkit? So instead of having every software developer have to say, what are the different ways that somebody can adapt my software, maybe that can be built into the toolkit. And so instead of building our own toolkit that has this kind of functionality, we instead decided to hack Cocoa, which is the toolkit used to build most Mac applications. So we built a toolkit called Scotty. And so this is a toolkit for making software more malleable. Let me show you a couple of examples of what I mean. So I've bought software, I've bought videos. So for example, here we have a video that I downloaded from the iTunes Music Store, or I guess iTunes Video Store, in the United States. And as is often the case in the United States, English is the only language. So there are no subtitles, there are no dubbed tracks, and so on. And I'd like to be able to watch this video with my colleagues or my friends who don't necessarily speak English or don't necessarily want to follow along with the audio without subtitles. It turns out that you can go online and you can find subtitles files. So we have a subtitles file that I found online and downloaded. But the software that's capable of decoding the encrypted video that I paid for from the iTunes Store is not capable of loading external subtitles. The software that's capable of loading external subtitles is not capable of decrypting the iTunes videos. So what we'd like to do is teach iTunes, or in this case QuickTime Player, how to add in external subtitles. So what we're going to do is go ahead and we can take a look and we see again, here's the video that I've downloaded, and here's the subtitle file that I've downloaded. If we take a look at that subtitles file, we see it's just a list of time codes and text that should be displayed on the screen. So if we go ahead and open up that video, we'll install the Scotty Toolkit on top of Cocoa, and that adds this extra button in our window. And if we go ahead and play the video, we see that as we go through, there are no subtitles. So we've got sound, but no subtitles. So let's go ahead and load subtitles. It's just going to look for the file with the same name in the same directory. And now we have them. And notice how the subtitles follow as I jump along in the playback, or as I resize the window, the overlay follows along, as if it were a part of the application. So that flicker that you were seeing is an artifact of the screen recording software that I was using. But anyway, so that works pretty well. Although, that does beg the question, okay, so I went ahead and I created this plugin, me as a programmer. I don't have access to QuickTime Player's source code. So how do I, as somebody who doesn't didn't participate in the development of this software figure out how I might be able to modify it. So the first part is trying to make sense of the organization of the existing application. One of the other features that we have, if we pull down on this menu, we can browse the widget hierarchy and use the existing user interface as a guide to the underlying implementation. So we see that we have one window. It contains one view, which contains two subviews. And notice that this subview is the disappearing, reappearing controller. We're probably interested in this one named MG Player View, whatever that is. We see that it's a subclass of Video View, NS View, and so on. And we can see that it introduces a couple of new methods. So if we go ahead and open up a Python prompt that's running inside of the application, we can go ahead and test this out. So let's go ahead and carefully place our window, load a little widget picker that lets us click on the window, and grab that control that we were seeing. So I'm going to go ahead and do that, click on the window, grab the MG Player View that we saw in the hierarchy. That's the one that's shown up there. And so if we store that in a variable view, we can go ahead and try out that player method. And we see that that does indeed give us something called an AV player, whatever that is. But that seems to bring us on the right track. And that happens to have a play method. If we were to inspect it in a similar way, we'd see that, whoops, let's store that in a variable, go ahead and start playing, and it's doing what we expect. So without actually having access to the source code, we can get a sense of the various hooks into the user interface that we need. We can see the current time in the playback, and then we can tell it to pause. And now we have the bits and pieces that we need to be able to connect the time codes that we have to the video. The rest is a small matter of implementation. All right. Let's look at another example of something else that we can do with this. So here we have, this is a web application that's running on my laptop in a multi-surface room. So I start this up. I might send the window to a tabletop. Maybe I want to interact with it on the tabletop or push it up and put it on a wall. My colleague grabs that on the wall, resizes it, makes it bigger so that it fits the size of the wall. As I interact on the computer, we see that it updates, and all of the updates on the computer are transmitted to the wall. Now, this is probably not amazing to most of you. We've all seen things like VNC, remote desktop, clients that let you transmit a window from one device to another. But did anybody see one of the problems? At the end, remember, the wall is a higher resolution device, so we need to scale that window up. Does anybody see a potential problem with that?
You have like lower resolution if you appear grainy on the screen on the wall?
Exactly. This wall is a much higher resolution display than my desktop. If I were to grab this and drag it and make it fill up the wall, I would basically see large, chunky pixels. This is an example taken from Keynote. And so if we look at this, we see that all of the text is just almost unreadable. Well, if you're sitting in the back, it's a little bit easier. And if you squint, you can make sense of it, but it's not really pleasing. Since this is running at the toolkit level, we have access to the underlying running application. So instead of sending the surface representation, the pixels drawn to the screen, we can actually transmit the underlying vector representation of these components. And so you can end up transmitting something that looks more like this, where the Bezier paths are nice, smooth Bezier paths. The text looks like nice, smooth text. And the raster icons still are bitmap images, and those are being sent to the screen. Although, if you take a look, for example, at this T, let me go back and redo that transition. Notice that that T actually has a little bit more detail, because what's being transmitted is the backing image and not necessarily the image drawn on the screen. So if the backing image is a higher resolution, you can actually transmit higher information that otherwise would be lost. So the idea is that what we want to be able to do is extend the toolkit with these new capabilities as if these kinds of interactions that really nobody knows how the user is going to really use the software so that they can actually adapt that to their own needs. So the Scotty Toolkit basically extends Cocoa with a couple of different kinds of components. The first are sense-making tools, so to help the third-party developer make sense of the organization of the existing application. Additional window hooks, because the window hooks in the application, in the toolkit that are already there, aren't designed around these kinds of modifications. Event funnels to handle redirecting input. Glass windows or overlays so that we can do things like glue subtitles on top of a window. And object proxies so that we can actually create object stand-ins. And in case you're wondering, Scotty is named after the miracle working engineer on Star Trek, who made the seemingly impossible possible, and also did the transporter so you can teleport windows to other devices. So let's start with the first of these. Sense-making tools. So we saw the first of these, which is, for example, the hierarchy browser that lets us look at the running representation of the application. And the idea is that most applications are already designed to be understood by the user. There's a user interface that the user should be able to make sense of. And so presumably, the underlying implementation has some sort of connection to the things that we see on the screen. So by navigating that user interface, we can peek down and see some of the underlying implementation details without having to do a full-on class dump decompilation and reverse engineering process on the entire application. And then the second one is the interactive Python prompt that lets us actually get in and start playing with these things and figure out and fiddle around and explore. Obviously, this is not something that I would be giving to my grandparent. My grandparents predate computers, so I think I'm okay saying that. I wouldn't make that joke about my mom because she was a hacker. So, anyways, let's take the second part, window hooks. So similar window notifications, drawing notifications exist in most toolkits, but they're designed around standard toolkit operations, and they're not really oriented around overriding the application. So for example, we might have a, well, hard to see, but we have window appeared. That's sort of a standard notification that you might be able to subscribe to within your application. But what we really want is that the window is about to appear. We want to know when the window is going to be drawn on the screen, but before it actually has, so that if we have any overlays that we want to do to modify its appearance, those will happen before the user sees it, so that we don't end up with any flickering effects. Similarly, we don't want to know when the window has been repainted and drawn to the screen. We want to know when the window did repaint and is about to draw to the screen. And finally, when the window disappears, we want to be able to intercept that right before it happens so that we can tear down any additions that we might have made. We can do that to windows, but we can also do that to arbitrary views within a window. And I got ahead of those animations. Next component is event funnels, and this one's a little bit simpler, but the idea is basically taking all of the different kinds of input events that can happen and redirecting them at the toolkit level to a new input handler that's just a generic input handler for arbitrary events. That's useful for example, saying, okay, I want to implement this with a state machine and have a state machine handle all of the management of my interaction. That way I don't have to hook it up into 500 different input methods. I can just hook it up to the handle event method. Overlay windows. So the idea of these glass windows is these are overlays that we can attach to different components. And these handle things like, for example, tracking as the window moves around instantaneously without sort of a lag effect, having that follow along. If the window gets resized, it's a part of the view hierarchy and basically does what you would expect it to do. And then the next to last part is dynamic code loading. So we've all seen plugins in a lot of applications. This adds plugin functionality even to applications that weren't designed with plugins in mind, such as, for example, QuickTime Player or Apple Pages or other applications that don't necessarily think about that. And it also gives us the ability to go down and replace existing method implementations. And we'll talk a little bit more about that through an example later on. Replacing method implementations applies to all instances of a class. Sometimes you only want to override the behavior of a single instance. And so in that case, we can create object proxies where you grab in the proxy object and use a forwarding pattern to basically override an individual method for an individual instance. So that's all well and good, but really this is sort of a proof of concept that really the person who's creating these modifications needs to be a programmer in sort of the Unix style of mastering a whole bunch of different independent tools that you have to have in your toolbox. And so in collaboration with Shen Zhao at the National University of Singapore, we applied these concepts and integrated them into Visual Studio so that you could, within Visual Studio, clone an existing application and use the existing interface builders to integrate these kinds of tools directly within that. So that the user no longer needs to be an expert at the entire system and maybe working with the entire manual and understanding in-depth everything, but could perhaps be just a regular, normal programmer. Regular, normal programmer, as if programmers were normal. Okay. So in all of these examples so far, the user is a programmer. But can we bring extensibility to non-programmers? Let's bring extensible interaction to people who don't need to actually build these. So can we change our mindset in building these tools to create ones where the user can adapt and appropriate them to create and compose their own interaction and their own interfaces? And so to do that, we created something called the grab and drop tool glass. How many of you are familiar with Toolglasses? All right, we have the computer science, human-computer interaction professor in the front of the room. So a tool glass is a bimanual interaction technique where the idea is, so bimanual, that means we have two hands. On our dominant hand, in my case, my right hand, we control the mouse cursor as usual. With the non-dominant hand, we have a second input device, a trackpad or another mouse, that controls a transparent overlay tool palette. And so to interact with this, it's a two-handed gesture. You bring the tool palette to your document, and you bring the cursor to the tool on the palette, and you click through to apply that tool to whatever is underneath that transparent overlay window. This takes a little bit of getting used to, but it's actually a really neat device, a neat interaction technique, and it keeps the interaction focused on the document instead of going back and forth between the document and a tool palette off onto the side. It was initially proposed over 25 years ago and hasn't really been adopted for a bunch of reasons, including, among other things, the fact that bimanual tools, so multiple input devices, are less common or were so 25 years ago. There are also patent issues, but 25 years later, hopefully those are going away, and so on. But as a result, most toolkits don't really have support, or applications don't have support for this kind of interaction. If we fast forward to today, many of you, even if you don't necessarily think about it, do actually, in many circumstances, have two pointing devices. So for example, here we have a laptop with a built-in trackpad and an external mouse. Oftentimes in these situations, we only use the external mouse, but there's no reason that you couldn't put your left hand or non-dominant hand on the trackpad and use your dominant hand on the external mouse. And most operating systems can handle that and treat those independently. So the hardware support has caught up, but the toolkit and application support isn't quite there. So we have two goals now. One is to extend the toolkit with Toolglasses for existing applications as is, so that they don't have to be modified to explicitly consider this kind of interaction. And the second part is that we want the user to be able to compose their own Toolglasses out of the existing components of the parts of the interface that they need. So there's been a lot of work on Toolglasses. There's the initial paper that introduced them. There's been adaptations of them that apply them to debugging operations, to visualization, and Michel Baudouin-Lafont and Wendy Mackay applied them to the CPN Tools 2000 toolkit for colored Petri nets, and explored a lot of really interesting interactions there. On the user modifiable interfaces side, there's been a bunch of work, for example, on WinCuts and WinSnippets that let users basically crop live windows so that they can just show the relevant portions, or maybe de-zoom them, and so on. There's user interface Façades that lets users recompose and change, for example, lists to radio buttons and different kinds of things like that at the toolkit level. This work basically introduces a proof of concept of the technique, a technical analysis of what is necessary and where it breaks down in existing toolkits, and also looks at conceptual compatibility between existing interactions and this kind of interaction. But let's take a look. Let's take a concrete look at what this does. So here we have an example of a list of paragraph styles that would be a part of a word processor, and we have an empty grab and drop tool glass. As the user moves around with their non-dominant hand, they can position, for example, an empty bin on the tool glass over a control that they might want to grab, move the mouse cursor over that control, and when you click on one of those empty buckets, it grabs that control into the bucket. And here it's basically just a screenshot of the pixels drawn to the screen. And then if you move that around, you've just lifted that representation into the tool glass. If we repeat that, we can populate that with the various styles that we might need to use. So we now have a tool we can use. So let's look at a concrete example of that. So here we're going to open up, it's an old video, but open up an older version of Pages, install the Scotty Toolkit into it. We're going to open up, for example, an unformatted text version of the article that we might have written as a draft. And now we want to go ahead and systematically apply the appropriate styles to the bit of unformatted text. So let's create our tool glass. We've got the text over here. We can go ahead and populate that with, for example, the title, the heading. We can grab subheadings, maybe normal body text. We can grab character styles, reset things to normal, or cross them out for editing. We can grab bold, italic from the toolbar. We can grab a font, and let's change that to a different font and grab that one too, as we might need in editing the paper. And now we can just go ahead and apply that just by clicking through, and in a smooth, fluid, two-handed gesture, migrate through the document like so. And let me just go ahead and skip forward. This works also even if we've hidden the controls or made them go away, because the tool glass actually captures those underlying controls. Okay. Oh, and we see that video continuing to play. So there are different kinds of interaction vocabularies that we often use with user interfaces. So one is that we often see, for example, subject and then verb. For example, when you're acting on a selection, you select something that you want to manipulate, and then you go click on a button or activate a keyboard shortcut or a menu item that applies to that selection. Oftentimes, we also see the opposite, verb then object. Enter rectangle drawing mode, and then click and draw that rectangle. So basically, if you're using a tool glass that's built around these existing components, you need to be able to support both of them. So right now we have just a really crude solution. All it is when you option click, when you're grabbing an action, it changes whether it applies the command before or after redirecting the mouse input to the underlying window. The implementation is a proof of concept. It's built on top of Cocoa using Scotty. And the idea is basically to say, what if Cocoa had this support out of the box? The implementation itself is fairly fragile, but we can imagine that if this were built into the toolkit, it could be made more robust. Now, there are certain requirements to be able to do this kind of thing. One is we need to be able to extract and invoke a control's associated actions. We also need to be able to handle hidden state and side effects. And finally, making these tool glasses persistent across multiple invocations of the application. For more details, please read the paper. But in Cocoa, some of this is actually relatively easy. So Cocoa uses a sort of MVC-ish architecture. It uses a target action pattern and dynamic dispatch. And so the conjunction of all of those lets us easily override method implementations and identify the various components involved in passing messages between a component, a UI widget, and the core functionality that's happening. So let's say that we have a button that does something. And it's going to have a bunch of objects in memory that who knows what they are. One of those objects is its target. So whenever the button is clicked, it's going to go to its target, and it's going to have an associated action do something that is bound to some method within that object. And so when we click on the button, it's going to call that method with, as a parameter, the thing that triggered the action. In this case, the button do something, the button that we clicked. So with those pieces, we can now capture the interaction associated with a given widget, even if that widget no longer exists, as long as we've captured a reference to its target and its action, and stored our own proxy for that widget. The next challenge is hidden state. So in this case, we see a list view. When the user clicks on this list view, maybe the callback, the target and action, might say, OK, list view, which row is selected? So if we have our tool glass that has the title captured, what we want is to trigger the title transition, so that when we click on that, it applies the title style. But if we don't capture any state, it's going to say, OK, list, what row is selected? It's body, and we end up transforming our body, applying the wrong action. And this would be kind of disconcerting to a user. So what we do is instead we capture a bunch of that state. So we've created proxies for the sender that let us capture that. So that for list views, we can capture the selected row, so that if we then later ask it, what is the selected row, our proxy can say whatever was selected at the time. We can handle segmented controls where there's a similar pattern. When you click, it says which segment is being clicked. And similar for these pull-down menus. And that's how the font menu that we saw earlier works and is still able to apply the correct font. That works because we created these proxies specifically for these kinds of widgets. We could imagine that if this were a fundamental part of the toolkit, that might not necessarily be necessary. And then the last part is we created a tracing proxy that lets us actually track, when you click something, what are all of the methods that are being called, so that we can figure out how we can create those proxies if we need to. Now, this is fragile. This has tons of limitations. There are the problems of hidden state and side effects. And there are also incompatible interactions. So one of the standard tasks that you might use a tool glass for is drawing. And it turns out that we've tested this in a whole bunch of applications. And for Keynote, OmniGraffle, and Preview, cases where you might want to draw annotations on a PDF or draw your slides or some sort of a vector graphics program, it turns out that this doesn't work at all, because the model that they use is a prototype-based drawing. When you click the button to drag out a square, it doesn't enter a mode, it drops a square somewhere on your canvas, independent of wherever the last click was of the mouse. And without hacking even more deeply into the application, it's just not really feasible to do that. So the UI interaction paradigms don't necessarily let us override that. That said, if this were a fundamental part of the toolkit, we could imagine that those applications might be designed differently. Sorry, a little French sneaking through. Okay. So far, these examples that we've been looking at are mostly in the world of desktop computing. So we've mostly been looking at a laptop, a desktop computer, mouse, and keyboard. But we don't really live in that world anymore. We have lots of small devices, watches, phones, tablets, slates, whatever you want to call them. We have wall-sized displays. This is one that we have at, bad resolution. This is a wall that we have at Télécom. This is another one. We actually have a network of these in Paris on what's called the Digiscope project. So we have 10 of these wall-sized interaction displays, each with different interactive characteristics, different resolutions, interaction capabilities. And so we have 2 of these at Télécom that have different kinds of approaches that we use. In this case, this is one that we have in our library so that students can come in, plug in their laptops, and appropriate the display and interact with this. But more generally, let's fast forward rewind into the 80s. And Mark Weiser's group at Xerox PARC explored a lot of blending of these different kinds of devices into common in common environments, where users sitting around this table, this gloriously 70s table, are interacting with tablets, with a pen, a laptop. There are tablets, there's the wall-sized display, as if it were a common unified environment. So if we look at these kinds of environments, you might have something like, for example, here we have a room with a tabletop, a wall, and some little red circles, motion capture devices. You might have one user in one of these spaces. He or she might be joined by a colleague. Maybe there are 3 people working in this environment together. They might each have their own interactive devices. So here somebody has brought in a tablet or a magic wand. And these red circles might actually be motion capture devices so that we can tell where different people or different objects are within this environment. And so we want to put this all together and create an environment where all of this has seamless interaction. So to really push these boundaries, we worked with some real scientists on some real problems, not our fake computer problems. And so in this case, this is working with, in collaboration with neurologists, where they're trying to compare healthy and sick brains. And so you have a neurologist who comes in with their data on their smartphone. They set it down on the tabletop to transfer the data there. Another person is interacting with this, organizing on the tabletop, the multi-touch table with its affordances, to organize those, while a colleague is working on the same data on the wall, looking at the higher resolution display, but that has no input capabilities in this case. Let's take a closer look here. And we notice that here he has, holding in his hand, a model of a human brain, and also a wooden chopstick from a local takeout restaurant. And what we've done is we've glued onto these motion capture trackers so that we can track in 3D space the position of the brain, the position of the chopstick, And so to look at different features of the brain, all he has to do is point to the part of the brain that's interesting, and all of the 3D models reorient themselves as if the camera were pointing right there. So that's a nice interaction. We actually built this. To do this, we needed to create our own toolkit. So we created something called Shared Substance that basically was designed from the ground up around how to build software for these kinds of multi-surface environments, where we have to manage shared state, what gets shared between different devices, each with different input, output, memory, computation characteristics. And how does the programmer express all of the synchronization and all of those challenges going along with that? So we built this system. I don't expect you to understand it from this slide, but if you're curious, please feel free to consult the paper. But basically, the challenge is that now you have to completely build all of your applications for this new world. Let's take a step back. Let's go back to the 1970s. Alan Kay had a vision of similar kinds of environments. So here we have two school children. Jimmy and Bethany are playing a game in the grass using their Dynabooks, which is, you can think of, at least in terms of hardware, as a precursor to today's iPads. They decide that their game is too easy, and so they decide, well, let's modify the game. Let's change the gravity in the game so that it can be a little bit harder, and so that they can have more fun. If we combine that with Mark Weiser's vision of all of these blended devices where they're all communicating, where we have different kinds of form factors, what we really end up with is basically something that we call shareable dynamic media instead of personal dynamic media. Instead of having just one user or a collection of users appropriating their devices, we have them all blending and working together. So we built a system called Webstrates. The idea is to build this on existing web technologies, to find a middle ground between hacking Cocoa, an existing relatively fixed toolkit, where you're very much constrained by the design choices around a single user with a mouse and keyboard and a desktop application, or something like Shared Substance, where you can build anything, but you have to build everything. And Webstrates basically lets us find a middle ground, where there's a lot of rich abstractions within the web ecosystem that lend themselves well to this kind of malleability. So we built Webstrates. This is this clay. It's sort of a clay to build these shareable dynamic media with shareability built in, support for asymmetric collaboration, and for malleability. So let's look at some examples of this. And I'm running a little bit behind, but that's okay. So here we have two web browsers, one in Safari, one in Chrome, and we see that as the user is typing over here, all of those changes are happening on the other browser. So two users that open up the same web page will see the same thing. The way this works is when the user goes and opens up a Webstrate, so a web page from the Webstrate server, it talks to the server that has a persistent database that stores all of the documents. It then injects into that page the Webstrates client, which then translates all of the stored objects on the server into DOM objects on your web page. The DOM is basically the document object model. That's what the web browser is using to render your page. If you have another user open up the same web page, their client is going to load the same objects and create the same DOM. If you change one of the elements of the DOM on this side, whether it's through some JavaScript application or just with the developer tools, then and the DOM inspector, then those changes get propagated through the client that listens on those, sends them to the server, and synchronizes that with the other open clients. Basically, you get a Google Doc for arbitrary web pages that are running on the Webstrates server. Now we can take this a step further and make this asymmetric. We can use something called transclusion, where we embed web pages within web pages that are live. So here we have, for example, maybe a slideshow. And so we have slides that are stored in the DOM, that are stored on the server, and then we have another web page that loads the slide editor, the presenter view, and as one of the things that it does is it transcludes, using an iframe, the same slideshow. And so now we have the slideshow being shown embedded within, and so in this case it's showing it as the thumbnail view and the current slide as the main view on the presenter display. By doing that, what we now end up with is the ability to have asymmetric collaboration. So here we see 3 documents. The main document that's not shown, so I guess we only see 2 of them. There's the main that's just the text of a document that we're writing. We see a WYSIWYG 2-column ACM layout representation of the article. And we see on the left more of a hacker mode editor with light text monospace font on a dark background. As the user types stuff on the top left, we see that those changes appear on the right, and we can adjust them live. In this case, this is one user using a preview and typesetting their paper, or sketching out a figure that is being sketched on the tablet, shown in an editor on the laptop, and we see the live sketch appearing as a placeholder in the paper as we're working on it. On the computer, we can now use appropriate tools to actually clean up the sketch and transform that into a proper vector image. Okay. The last part of this is malleability, and so and extensibility. So in this case, we might say that Alice on her editor has decided that I have a citation manager that integrates with my bibliography, and Bob on the right might say, oh, that's really cool. I would like to extend my completely different editor that uses a different representation with that capability. And so we can copy the reification of that instrument, of that editor, from Alice's interface and just go ahead and paste that right in on the right. And so now we're basically extending a different editor with capabilities dynamically from whatever was in the other one. Now, we can also extend this. I don't have a video to show this, but this same technique applies to, okay, we've been using this on our paper. Now we have to create a slideshow. Why can't I use my BibTeX citations in PowerPoint? As I'm just saying, oh, on this slide, I need to remember to cite Wakaranamathon. I hope I got that right. In our paper, or as I'm sending emails to my students, the same thing in an email client. There's no reason that I shouldn't be able to extend my email client with such integration. And that brings us to the very last point that I want to make, which is what we've seen here is that users appropriate the tools that they have to cope and manage. A lot of work that we do is about learnability from the first time anybody uses a piece of software perspective. How does somebody walk up and use software without knowing how to use it? That's important. If you're creating the new kiosks at the train station, that's going to be an important thing to do. But if you're creating something that where the tool is intended to be mastered, maybe we need to go a bit beyond tricycles to bicycles, where a bicycle is actually an unnatural interface to learn. And yet, if you spend the time to learn how to ride a bike, it can be a great, flexible, and powerful tool. And so right now, we're sort of stuck with these tricycles. So I want to just leave you with this idea that in these examples, we've been looking at programmers modifying these things. But remember that users are not alone. They're interacting in an ecosystem with other users who have different skills and different levels of motivation. And so you may have your casual user who doesn't want to have to fiddle with plugins and the like, but they may have a colleague who likes fiddling with those and can make modifications and share them, or somebody who can actually build and actually fiddle with code and can do so. And so this is more of a continuous spectrum. So in the same way that with physical tools, we might be able to take a terracotta pot and turn it into a kiln with a couple of bricks and a thermometer, maybe we can have people who, the first person who needed to use a pair of pliers in a tight space probably had to hack up their tool. And then now they said, hey, that might be useful. And so this is something you can now go to the local hardware store and buy. Or similarly with these screwdrivers. Or we can make general purpose gadgets such as this adapter for a grinder, where regardless of whatever tool you want to sharpen, you can adjust the angle and have something so that it's basically, I don't have to have fine motor skills to find the right angle. I can just use the adapter that simplifies that task. So I'd like to leave you with this, this notion that the computer is a tool for interacting with data, but what we really need to do is foster the human skill and appropriability and masterability. Today, we're still riding tricycles, and we need to move past these tricycles with training wheels, I'm mixing metaphors here, so that we can foster mastery and give users a real sense of ownership of the tools that they're employing. This is work that's been done with a lot of people that I would love to thank. So Wendy McKay, Michel Baudouin-Lafont, Clemens Klockmose, Shen Zhao. We have great PhD students working in the DIVA lab at Télécom Paris. There are 3 of us in our research group, as well as some associate members of our team. There's soon going to be 1 more starting in January. And we're also looking for, if any of you are not planning on doing a PhD here, we are hiring PhD students to work more on the design and data visualization side. Thank you very much. I would be happy to answer your questions.
Thank you very much, James. So now we have time for some questions. I would like to ask you to maybe repeat the questions. So
sure.
it is also recorded. So while you all are thinking about burning questions, I have the first one to ask. Because you have experience of designing the software to make it malleable, but how would this change the design process? Because nowadays, if we want to design software to support specific tasks that the user is doing without the software, we go observe that users, right? But now you are designing the software and you expect that the users will change or adapt your software. You cannot observe anybody doing that. So what is the change in the design process?
Okay, so I'm going to try the short version of that question, which is how does this influence the software design process, and particularly in terms of doing user observations? And so in some sense, it doesn't. That's still absolutely necessary. The idea is that these software tools really ought to be something that, if you're creating a product, it should be designed for the needs of most users, or at least the target population of users. And so all of the existing stuff that we know about how to design good software interfaces, that sticks. The added challenge is it actually makes implementation a lot harder, because now there's a lot less that you can take for granted. For example, the grab and drop tool glass that we saw there, suddenly if you have something that breaks the core implementation assumptions of the underlying application, it might enter into an unexpected state and crash. So the thing that needs to be added on is more of a consideration as we're building software that maybe a lot of the assumptions that we're making don't necessarily hold. I would argue that a lot of those assumptions go away when you use good design practices and good coding practices, we all know that reality is that that's not the case. We would all be horrified to look at the implementations of our favorite software packages, and we've all written our own software that we'd be horrified to look at.
Thanks. Any questions from the audience? View your software. Yeah.
You mentioned in the beginning that in the 80s, if I recall correctly, there was more research into making the software malleable by the end users, and that has sort of been abandoned.
Yes.
Do you have any insights into why the approach failed or was thrown under the carpet back then?
Okay, so the question was that I said earlier that in the 1980s it seems like there was a lot more research into the sort of malleability kinds of work, and that there seems to be less and less of it today. And the question is, do I have any intuition as to why? Anything that I say is purely conjecture. I have no data to support this. But I suspect that part of it has to do with the focus more on usability and beginner usability of software, and moving less towards expert masterability of software, where it's just hard enough to get things that are simpler and simple, easy to use. And if you have to then say on top of it, okay, and how can I extend that? That is a much harder challenge. So I think part of it is that the commercial pressures have steered in that direction. On the flip side, there was one of the things that was going on is back then, in order to be a computer scientist, you really had to master the entire system. So for example, some of those names we were talking about, Xerox PARC, Alan Kay was at Xerox PARC, Mark Weiser was at Xerox PARC. The Xerox Star, which was one of the precursors to today's Macintosh and Windows systems, basically those all have a common genealogy. That's not to say that there weren't other people working on similar kinds of things, but a lot of the genealogy of the stuff that we use today goes back to then. There, they had to work on the hardware, work on the operating system, work on the programming language. Depending on who you ask, Alan Kay was a programming languages computer scientist, or a human-computer interaction scientist, or the pioneer of I'm blanking, but depending on who you ask. So basically everybody had to wear multiple hats, and so you could then have somebody who's using your computer. You could expect that maybe your secretary might not necessarily be a hardcore programmer, but is not necessarily afraid to look into a configuration file and maybe write a couple of lines of Lisp to extend their, to create a new widget on their desktop. I don't know if that makes sense.
Yeah, no, so it's more about that it wasn't as democratic back then, that even enough people would have interacted with the systems for this to be interesting.
I think that might be part of it, but I'm just speculating.
Yeah.
Yes.
How do you deal with self-learning according to behavior?
Self-learning according to behavior. So I'm not sure if I'm answering the question that you asked, but one of the things that is really interesting about web development is that at least today, and this is becoming less and less the case, but at least today, a new user can take a web page and say, oh, that does something interesting. How does that work? And can sort of lift the curtain and look behind the scenes and see the wizard that's making all of that work, play with the source code, try things out, and basically sort of discover on their own different ways of doing things. In some of the older work I was alluding to, for example, the Xerox buttons work, where a secretary might be able to create a widget on their desktop using a couple of lines of Lisp, that all of those widgets, you could also take an existing widget and peek behind the scenes and see how it's written. If you've ever used Squeak or Smalltalk, one of the things that's really cool is you can basically take a running component in your user interface and you can peek behind and see the running state and the running code and modify that live. And so that reduces a lot of the barriers to between what it means to be a developer of an application and a user of an application. Those are some things we try to address in some follow-on work to Webstrates, but it's still very early. Did that answer the question?
It's one answer.
Okay.
We take one last question.
So do you see a certain conflict between your concept of malleability and maybe, I don't know how to call it, a consistency of an interface, you know, especially if you think about a program that you only use rarely and then somehow you make a button disappear and you can't find it anymore and so on. I mean, this has happened before, right? So
Absolutely.
Like, aren't these technologies some fun?
Absolutely. Right now, for a lot of commercial reasons, and they're very legitimate, a lot of companies don't want to have users going around and massively reconfiguring their interfaces because it just increases the surface area of bugs and user support needs. On the other hand, there is also sort of a trade-off. That means that we're basically sealing the car engine so that nobody can go in and add a turbocharger. Okay, maybe that's a bad example, but you know, use a different brand of headlight in their car. So there's definitely a tension. There's a trade-off there. Did that answer the question? Okay.
All right, so thank you very much, James. And if you are interested or would like to ask more questions or talk to James later, we have apero outside. Yes.
Great.
Let's give James a
Thank you. If you'd like to talk about this, or if you would like to talk about how people make sense of data, if that's more your cup of tea, please feel free to talk to me during the break.